Did want to go over these couple of announcements. I know you've heard them and it really doesn't pertain to you, but I still need to get them said so they can take care of it if they need to. Last week, sometime late last week I think it was, the Vice President sent out an email saying that as of today, any student who's not paid for a class is going to be removed from the class, okay? So what that means is if you are, if you even know someone who may not have paid for a class, please let them know they've got to get something done before the end of business today. Now, preferably that's paying for the class. But if they can't pay for the class and they're in the works and, you know, something else can happen, then they need to go by the business office, which on this campus is the cashier's window, and let them know what the situation is. They may be able to put a flag on your record to keep them from being removed from the class. So I wanted everyone to know that so they could tell all friends or anybody else, please get it done today. Absolutely. All right. Next thing, I guess, was I don't know if it's a big deal or not, but normally on Fridays I have office hours from 7:45 to 11:45 on the Bessemer campus. Not this week, because they've called a meeting on the Birmingham campus. I said Birmingham campus. They've called a meeting at 12:30. So therefore, my office hours are actually extended 7:45 till between 12:15 and 12:30, because I'll need to be going over to the meeting then. So if you need to see me, I'll be on the Birmingham campus, room B122, between 7:45 or so in the morning until about 12:15, 12:30 in the afternoon. And then I'll be at the meeting, and then after the meeting, I'll be heading home, hopefully. Okay. So, then the other thing, math team going to meet this afternoon, 3:15? First time. All right, we'll get it done. I have a student coming by for advising. No, he can't come by at 3:15. That doesn't bother the math team. I'll have to. Oh, wait. You don't have physics class today. Dr. Bryant called in. I don't know if you noticed Monday, he sounded pretty like stuffed up. He's worse today, so he's not going to be coming in today. Yeah, he sounded terrible on the telephone, so he won't be here today. Well, he said he hadn't gotten to a working computer yet, and I think he's feeling so bad, I don't know if he's going to even make too much of an effort to get to a working computer, but anyway, he said put it on the board. And y'all have been meeting in here. Okay, I'll put it on both boards. Well, I'll put it on that board, and then if anyone comes in here, I'll tell them. What's that?
I said, basically, I need to work on my case.
Yeah, he said y'all had an assignment already. Yeah. Okay. All right, so I guess that's about it. Let's get started where we left off last time. Any questions on anything we've done so far?
What station is I got my book today?
So which what?
Which station?
Okay, we're starting in 13.2. And I hit the wrong key. And we just got started on 13.2 last time, so we're continuing on page 697. And it's vector value limits are computed component-wise. And we had started talking about calculus of vector value functions. And, of course, the first place to start usually in calculus is with limits. So if you have vector value limits, they are computed component by component by component, which is what you do just about everything with vectors in. Do it by components, and everything works out much better. Okay, so vector value function, R of t, it's a bold R, so it's a vector value function, and it's components of that vector value functions, x of t, which is a scalar function of x, scalar function of y, scalar function of z, with the parameter t. The vector value function r of t with those components approaches a limit as t approaches t0 if and only if each of the components approaches a limit as t approaches t0. So, and if it does, if each of them do approach a limit, then the limit of the vector value function, r of t, would be the components. Limit of x of t as t approaches 0, the limit of y of t as t approaches 0, and the limit of z of t as t approaches 0. Those would be that would be the limit of the vector value function as you take the limit of each of the scalar value functions that are your coordinates, components, of the vector. Okay, they have a little proof there that starts out with this line here. Which, if you think about it, starts with let U be a vector ABC, and then consider the length of the square of the length of the difference between R of t and U of t, and this would be R of t, which is x of t, this first component is x of t minus a plus squared, y of t minus b squared plus z of t minus c squared. That's where you begin the function, and you go from there. And Victor's here. All right. Just a couple of things. First, and probably foremost, were you here when I announced about today being the deadline for anyone to pay tuition? Okay. I know y'all are okay, but if you know of anybody who may not have completed payment for this term yet, please let them know they need to do something today, okay? Because as the end of business today, they're going to be purging the rolls of all non-paid students, or at least that's what it was said in the Vice President's memorandum. So please, if you know of anyone who may not have completed registration yet, they need to do it today, okay? Now, even if they can't pay the full amount today, they need to go by the business office, which on this campus is the cashier's window, and let them know what their plans are. Because they could, and I was told they are doing it on the Birmingham campus, so I'm sure they do it here too, they could flag your account so that you won't get dropped from the roll. So if you know of anyone in that boat, go for it. And the other thing is the math team is going to meet at around 3:15, sometime after 3:15 today, and we'll go as long as you want to go today. Because you're not in physics, are you? Okay. The physics class, Dr. Bryant is sick today, so it won't be meeting today. Okay. But this was the second line of the proof of Theorem 1. I won't go into the whole proof, but that's how it begins. Okay. Then the next thing you hit is example 1, which they don't have anything for, so let's do example 1 here. Okay. Okay. Calculate the limit as t approaches 3 of r of t, it's a vector valued function, where that r of t is equal to vector components t squared, comma, 1 minus t, comma, t to the minus 1. Okay, there's the vector. Now, why did they write R of t twice? Why did they just write this in there and it'd be so easy to do, but still easy to do? What is that limit of this R of t?
So you said the limit is just the limit of each component?
Yes. So that would be 9, comma, negative 2, comma, 1 over 3. That's it. Okay? Seems like there was one other thing I was going to add to that. Okay. Through already? Okay. Those are the two taking the test. Okay. Let's see what's there. Okay. Whatever I was thinking of saying about it, I don't recall now what it turned out being. But if it comes up, I'll pop it again. All right. Now, the next thing they address is continuity of vector value functions. Okay? Now, for instance, is that R of t a continuous function? Why not? Okay. Usually continuous functions do have limits. Actually, there's one place it doesn't have a limit. That would be what keeps it from being continuous. Where would that not have a limit? Second? The R of t. What value of t is that not continuous? Not down here, the R of t up there. Here's your R of t as a function of t. This basically is R of 3 there. Second? No. That. Where is that not got a limit? At 0. You can have 0 here, that would be 0. You can have 0 here, that would be 1. But you can't put a 0 there, because that's 1 over t, and you can never divide by 0. So that one is not a continuous function at t equals 0. Now, if you're anywhere from negative infinity to t equals 0, but just not counting t equals 0, continuous all there. If you're from 0 to positive infinity, but not counting 0, continuous everywhere there. But it's not continuous across 0. Okay. So you cannot have 0 in the domain. Everywhere else, that's continuous. All right. So that's what we mean by continuity. Continuity of vector value functions is defined the same way as the scalar case. A vector valued function R of t, which is x of t, y of t, z of t, is continuous at t0 if the limit as t approaches t0 of R of t is equal to R of t0. If it's not, then it's not continuous. Okay? That would not be as t approaches 0. Anywhere else is continuous. As t approaches negative 5, that's continuous. As t approaches 15 halves, that's continuous. But not at t equals 0. Okay? 0 equals 0. Not continuous there. Okay, so that leads then to this. Sort of indirectly, but it gets you there. Okay? The first derivative of the vector value functions, guess how we're going to take the first derivative? Second? Okay, yeah, you ultimately do it by components. Just about everything with vectors, treat them by components. Okay? So the r prime of t would be d by dt of r of t, and that would be the limit, just like you're saying, of the limit is h approaches 0 of r of t plus h minus r of t over h. Same as our definition for scalar functions. It works here too, but the big key is do it by components. Okay? They do say one more thing here, which they almost say here, and this is the same as dr dt. To me, that's what this says, but they want to make a special note that it is that. Okay, now, r of t is called differentiable at t if the limit of this equation exists as t approaches. Sorry. As t approaches. All right, sorry. I'll get it back soon. If that limit exists, okay, we'll just say it that way. Notice that the components of the difference quotient are themselves difference quotients. And that's what I was leading to. I jumped the gun on it just ever so slightly. But this is where we're leading toward. Vector value derivatives are computed component-wise. Everything you do with vectors, pretty much, do it by components. Okay? Vector value function R of t, which is a, t, y, t, z, or t is a component. That's differentiable if and only if each component is differentiable. Okay? So R prime of t, which is dr dt, would be x prime of t, comma y prime of t, comma z prime of t. If each of those is differentiable, the vector value function is differentiable. Okay. Now, they kind of skipped example 2 and stuff leading up to it. So let's do a couple. Here are some vector value functions computed component-wise. First thing they asked was d by dt of, actually, better to write that, d by dt of the vector t squared, t cubed, comma sine t. You tell me what that derivative is. Hint, it will be a vector. What will be its components? Two t, 3t squared, cosine t. All right, got it. About this one, d by dt of the vector cosine t, comma, -1, comma, e to the tt. Can you take the derivative of that? Second? Okay, then this will be a vector. Negative sine t is the first component, comma. 0 is the second component. Whoa, what in the world is that? It's supposed to be a comma, and it just went wacko. Okay. I think my top here shimmered. Okay. That's it, exactly, 2e to the 2t. Chain rule going into effect there. Derivative of e to the 2t is e to the 2t. Then you do the chain rule and take the derivative of the innermost part, which is the derivative of 2t, would be 2. So that goes in front. Okay? Very good. Now we're, okay, higher order derivatives are also defined by repeated differentiation by components, component by component by component. So r double prime is d by dt of r prime. R triple prime is d by dt of r double prime. Okay. So I don't think I need the space. I'm sorry. But in case I do, I'm going to erase it. Everybody got this? Yeah, okay. Calculate r double prime evaluated at 3. So this is what we're looking for. R double prime evaluated at 3, where r of t is equal to log t, so vector, log t, comma, t, comma, t squared, I think it is, yeah. Okay. Goodness, my head's hurting. Okay. Now, what do you do first? Take the first derivative. So first let's do r prime of t. And we keep the t's. You don't ever plug in the value until you get to the last step. Okay? So what would this be? That's ln of t, right? What is the derivative of that? That's the inverse of it. What did you say? 1 over t. That's it, exactly. 1 over t, comma, 1, comma, 2t. Close. There we got r prime. What do we do next? R double prime, again at t. Keep the t in there until you got it done. Now, I'm going to slightly rewrite that first one, the first derivative. Instead of 1 over t, because I don't like differentiating things with the variable and denominators, I like to write it as t to the minus 1, comma 1, comma 2t. Okay? So let's take the derivative of that. Negative. Okay. Okay, negative 1 over t to the t squared. Okay. All right. Now, I don't like trying to do it this way. You could. I like doing it this way. That would be minus 1 t to the minus 2. T to the minus 2. Okay. That's the first one. Second, 0. Third component, 2. Okay. Now we plug in the 3. R double prime of 3 would then be what? Negative 1 over 9, comma, 0, comma, 2. Because those are constants, you just keep them. You know, they plug in. There's no t dependence. All right. Let's see if I can find where that was. Here it is. And that would be negative 1/9, 0, 2. Good for them. Goodness gracious. Okay. great day. Goodness, we just have gotten started and my eyes are just doing weird things. Sorry about this. Let me run down. I was asking when he could pick up his test. Okay. All right. That was example 2. All right. So we're ready for this, differentiation rules of vector valued functions. And guess what, team? There's not a lot of difference here from what we've done before. That's the beauty of it. It's pretty much the same as before. Differentiation rules assume now that R of t is a vector value function. R1 of t is a vector value function. R2 of t is a vector value function. And they're all differentiable. Okay? Then, start with the sum rule. If you have the sum of two vector valued functions, you're taking the derivative of that, if that's the easy way to do it, do it. But if it's easier to take the derivative of the first and then add it to the derivative of the second, you can do that because the derivative of the sum of two vector value functions is the sum of the derivatives of those two vector value functions. So whichever is the easier way to go. Constant multiple rule. Okay? For any constant c multiplied by a vector value function R of t, if you take the derivative of that, you can pull out the c and take the derivative just of the function. Just like we did in everything we've done, with derivatives. Product rule. Okay? Now, this is a somewhat limited product rule so far. For any differentiable scalar function f of t, not a vector function, vector value function, a scalar function f of t, then the derivative of the product of a scalar function and a vector valued function would be the scalar function times the derivative of the vector value function plus the derivative of the vector value function times the scalar value function times the vector value function. It's your product rule like we had before. Product of two scalar functions is the first time derivative of the second plus the second time derivative of the first. With that, one being a vector, one a scalar, it still works that way. While I said it's a little limited, we aren't even talking about a product of two vectors yet. Okay? So don't, because there's two kinds of products for two vectors. You may have run into them before, have you? Dot products and scalar product, cross product. Dot products and cross products. So we're not there yet. We're just vector value function times a scalar value function. Chain rule. For any differentiable scalar value function g of t, if you're doing the derivative of a vector valued function of a scalar value function, then what you do is take the derivative of the outer one at that same value and then multiply it by the derivative of the inner one, the chain rule, just like we've done before. And don't even think about putting a vector value function in there way beyond the level of this course, if that's even defined. I can't recall now any way to really do that. So we'll hopefully see some examples of that. Okay, so there are your differentiation rules, and you'll notice very similar to the regular kind. Just the product rule is only the product of a scalar function with a vector value function, and the chain rule is a vector value function evaluated at a scalar value function, taking a derivative of that. All right. Now, they're skipping example 3. So let's go back and do that first, and then we'll get down, I didn't know it was coming up this soon, dots and cross products, okay? Said we weren't there yet, we'll get there really soon. So let's do example 3. Let R of t, vector value function, and let it be t squared 5t 1. Okay? And f of t is equal to e to the 3t. All right? It says calculate first the derivative of d by dt of f of t r of t. Oops. So used to doing angle brackets. I put one where it doesn't make any sense. Okay. There. So let's do this first. We've got, how did that comma get in there? I think my pen slipped or something. That's not a comma. I think that I was trying to continue there. Derivative of the product of the scalar function, e to the 3t, multiplied by the vector function, r of t. Okay? How would you do this? What's that? Okay. There's a vector value function, t squared 5t1, okay, components. Your scalar value function, f of t is equal to 3e to the 3t. What we want to do is take the derivative of the product of the scalar value function times the vector value function. How do you do it? Yeah, product rule. Okay, so that would be e to the 3t times, which is 2t 5 0. Okay? Which is, what's the derivative of f of t? 3 times e to the 3t times t squared 5t 1. Okay? So, what will this become? What's that? Yeah, I was just trying to think the best way to do that. I'm not sure there is a best way, but let's put it all in vector bracket. This will be a vector. Okay? The first component here is 2t e to the 3t plus 3t squared e to the 3t, comma. You did the first terms, right? Yeah, you're adding vectors. You add component by component. Okay? Comma. Five e to the 3t plus 15 t e to the 3t, comma, 3 e to the 3t, done. Okay. Now, whether you had to write them out that way or not, I don't know. It just seems like the most reasonable way to do it. in some sense. This is ugly here. Let me see if I can erase it. There we go. All right. My temptation would be every term and everything has e to the 3t in it. So I think I would have been tempted just to e to the 3t. Pull that out. 2t plus 3t squared, comma, 5 plus 15t, comma, 3. That would have been a lot shorter to write. But I didn't know which way the book wanted it, so I thought, let's do it in gory detail. Let's see how they did it. They did it in gory detail, okay? And for some reason, they reversed the order, but they put, well, they factored out the e to the t in each term, which was okay, too. So they said 3t squared plus 2t times e to the 3t, first component, comma, 15t plus 5 times e to the 3t, second component, comma, 3e to the 3t, third component. Okay. So you see there's several ways you can write these answers. And again, that's, to me, a screaming indictment against these computerized programs that you do homework in, like WebAssign and stuff like this, because they're looking for one right answer. And you can write about, we've already done 3 right answers. There's a right answer. Actually, the one above is a right answer. This is a right answer. And the one in the book's a right answer. And that's not all of them. You could write them in several different varied forms and be perfectly correct. And those packages would say, wrong, you know, and you don't know that you got it wrong because you wrote it in the wrong form or you just didn't do the math right. And it's pretty frustrating. Okay, that's my soapbox. Let's do the B part, and what I'm going to do is erase this that I did at the bottom so I have room to work down here, and hopefully I can get this one done too. Here's the B part. The B part is asking for us d by dt of r of f of t. Sorry. Now, I wanted a little time out first. I'm going to say this before I wrote that one down. What you could have done, I'm not saying it's any better, worse, or indifferent or anything. You could have actually multiplied this to begin with. In other words, e to the 3t, t squared e to the 3t, comma, 5t e to the 3t, comma, e to the 3t. That would have been the product of these two. Then you could have taken the derivatives of that. Well, you have the product rule to do each term, so you wind up doing the same thing. It's probably just a hair easier, more direct to do it this way. But you could have done it the other way, is actually multiply these two together, then take the derivatives. Okay? So, not particularly hankering to do that to show you it's the same, but you could have. All right, now what do we do with this? Now, one thing I left off my vector, because that is a vector. My eyes are doing it again. I splashed them with water, and they felt a lot better. Now they're not. Okay. So, what do we do with that? Say again? The chain rule, and how does that go? F prime of t R prime of g of t. I'm sorry, f of t. I was looking at the thing above, not at what we're really doing. R prime of f of t. Okay. Now, we got to figure out what in the world that means. F prime of t is pretty easy. What's that? 3 e to the 3t. That part's easy. What in the world do we mean by r prime of f of t? Okay.
You have to take the derivative of r and then substitute.
Say again. Okay. Yeah. Now, I don't know if this is what you were saying, but you take the r prime of t, okay, except everywhere you see a t, you put in f of t, right? Okay, so if you followed what I meant there, that first part was the easy part. Now this part, let's do, and in fact I'm going to write it down. R prime of t is going to be what? 2t, 5, 0. Oh, we had already done that, hadn't we, somewhere up there? Oh, that was in the first part. Okay. All right. Now, so what we do here is, there's your f prime of t in front. Your r prime of t is exactly that, but it's r primed of f of t. Okay? So the first component is going to be 2 e to the 3t, right? Comma 5, comma 0. That's all it is. Okay, now, if you want to combine that together, you don't have to, but you could. That would be 6 e to the 6t, right? Comma 15 e to the 3t, comma 0. Okay? Now, let's see how they did it. The B part, 6 e to the 6t, comma 15 e to the 3t, comma 0. They did combine it at the end. All right. Now that said, we could have also done that with this, okay? When we're doing r of f of t, here's your r, and everywhere you see a t, put in this instead. So that would have been a e to the 3t squared, which would have been e to the 6t, right? Plus 5e to the, comma 5e to the 3t, comma 1, okay? And then take the derivative of that, you'd have gotten the same thing, okay? So it doesn't really matter whether you plug in what this is and then take your derivative, or use the chain rule and do the derivative that way. You'll get the same answer. Usually the chain rule, I'd say most of the time it's going to make it a little easier. All right. Now, as I said before, this product rule was only for functions times the root of scalar functions times vector functions. And it doesn't matter the order, you can do it either way. Okay? And I said there are two kinds of products of vector functions, dot products and scalar products. And, sorry, I keep saying that. Cross products. Okay? This next thing tells you what to do for those kind of products. Not scalar times a vector, but vector dotted with vectors and vectors crossed with vectors. So here's the product rule for dot and cross products. Assume that R1 of t is a vector valued function and R2 of t is a vector valued function, and both of them are differentiable functions. Now, for the dot products, the derivative of the dot product of these two functions, R1 of t and R2 of t, both differentiable functions. Just what I hope you would expect the product rule to be. The first times the derivative of the second, dotted with the derivative of the second, plus this second dotted with the derivative of the first. They do first derivative of the first dotted with the second. The order doesn't matter in dot products, okay? It doesn't matter as long as you get the dots done, okay? Now, what is the result of the dot product of two vector varying functions? What will a dot product always produce? A scalar. You lose the vectors. So if you dotted these two, you're going to get a scalar. Derivative of a scalar would be a scalar. Well, guess what? Dot these two, you get a scalar. Add to that the dot of these two, which is a scalar. You still got a scalar. So yeah, at least the type of functions those are consistent. That will be a scalar function. When we get to cross products, okay, hopefully it's just what you would expect. It is derivative of the cross of two vector value functions will be the first one crossed with the derivative of the second plus the derivative of the first one crossed with the second. This time you can't say, oh, the order doesn't matter. It does matter. You have to keep the R1, R2, R1, R2. You have to keep that order there. And the derivative. Now, one place it doesn't matter, you could have done this one first and that one second, because adding doesn't matter. You know, addition of vector value functions is commutative. It doesn't matter what order you add them. It does matter what order you cross them. Doesn't matter what order you dot them, but it does matter what order you cross them. So keep that in the right sequence. I'm used to saying it, as you heard me say earlier, the first times derivative of the second plus the second times derivative of the first. That's how I like to remember the cross product. The product rule for regular functions. Okay, it's just easier for me to remember that way. But you can't do it that way in cross products. It's the first time derivative of the second, cross the derivative of the second, plus the derivative of the first, cross the derivative with the second. Okay? And the reason for that, if you change this order, you negate your answer. So you'll introduce a negative sign that's not supposed to be there. Okay? So, stomp, stomp. Okay. Now, in this chapter, all vector value functions are assumed differentiable unless they're otherwise stated. And then I would also say, unless it's obviously they're not. I don't think they'll do many of those. Now, I don't think no. They don't have anything for example 4, so let's do example 4 on this slide. Okay. Oh boy. Prove the formula that d by dt of r of t crossed with r prime of t is something else, okay? And it is r of t cross r double prime of t. Okay? That's what we're trying to prove. Is it even true? Okay? Let's start with the left-hand side and do what they tell us to. What is this thing? Anyone got an idea? From our cross product rule below. What would that be? expression. Okay, it would be, I'll open a bracket, R of t cross R double prime of t. Okay, now notice what? Okay, that's an equal sign of it, not a double prime. I was going to say, what is that? It's just an equal sign. Okay, when you're doing a cross product of two vector value functions, it's the first one cross the derivative of the second. What we're doing here is the cross product of derivative of the cross product of that function cross that one. So it's this function cross the derivative of the second function will be the second derivative of the function, right? Plus, okay, we'll put that in bracket like they do. You really don't need to, but we'll do it just for illustrative purposes. Now, remember, you got to keep the order the same. That'll be plus R prime of t, right? Okay, cross R prime of t. Okay, derivative of the first cross with the second. Okay, the first one was R of t, so its derivative is R prime of t. Cross that with the second one, which is already R prime of t. Okay. Now, there is a feature of cross products that is pulled in to determine here, okay? And that is, let's go back to dot product for a minute. Dot product of two parallel vectors, two vectors going in the same direction, it's just the product of those two vectors, okay? Okay. Dot product of two perpendicular vectors is 0. Dot product of perpendicular vectors is 0. Now, for cross product, the cross product of two parallel vectors is 0 because you can't, the definition is, part of it is magnitude of one times magnitude of the other times the sine of the angle in between. Sine of 0 is 0, so that produces, this thing produces 0, okay? A vector crossed with itself is always 0. So this goes to 0, so you wind up with this, which is exactly what that is, okay? So that's all it was to prove that. But the cross product of a vector with itself is 0. Now the interesting thing here is that even though they said we have to because it says here this plus this, and I was emphasizing the cross product order has to be the same, but I said the sum never is, okay? You don't have to keep it the same. What they did in theirs, they did this one, they did that one first and this one second, because addition is commutative, so that didn't matter there. I did this one first because that's what the rule said, but the rule doesn't care about the plus sign, it just cares about the cross products. As long as you don't change those orders, you're fine. Okay. Now, I think That's all we got for that. Now let's look at derivative as a tangent vector. Now I think we've been talking about them and just assuming that's what it is, but this sort of validates that assumption. Okay? All right. I did blow that up, didn't I? It was so small. If you have a vector value function, actually I like the illustration first, then I think I'll come back to this. That makes it just easier to do. Goodness gracious, when are they going to ever get to this illustration? There it is, finally. Okay. Okay. All right, here we go. I don't remember, now if you remember, we called them difference quotients. You know, back in pre-calculus algebra, again in calculus 1, we call them difference quotient. They're using that term again. Okay, now, here's some vector r at t0. Sometime later, t0 plus a little bit, h. Now your r is over here. Okay? Now, r of t0 plus h minus r of t0 is going to be this vector right here. R of t0 plus h minus r of t0 is that vector there. All right? Now, that's beginning to look sort of familiar, like your limit type thing. In fact, the only thing you're going to do to make this look just like what's inside the limit is divide by h. Now, of course, remember, if h is a very small number, and you divide by a very small number, that's like multiplying by a pretty big number, right? So, this would be the vector that when you divide by a number less than 1, it actually extends the length of that. That would be the actual value of the difference. Then when you divide by a small number, which is like multiplying by a bigger number, you get the same vector, but with a scalar. You know, you've extended it. Okay. So that's what goes into, that's what we call delta R. Delta R is the change from this to that. This minus that. That's your delta R. Okay? Now, with that telling you what delta R is, keep that in mind. Let's go back to here. And what we're talking about doing here is doing delta R over delta T. Okay? Okay. A little tricky here, but it's doable. Your T is, of course, this value, but that's also a T value. So delta T would be T plus H minus T0 plus H minus T0. Well, the T0s go out, you're left only with the H. So this is indeed your delta R over delta T. That's your delta R, your delta T is H. It's written in that form, that's just H. Alright? This is beginning to look a little like a derivative, especially if you take the limit of this as delta T approaches 0, and take the limit of this as H approaches 0. Yes, you've got exactly your first derivative. Okay? Now, that's where this comes into play. Still think they've skipped some stuff here. What then is a tangent line at r of t0? Vector value function at t0. Okay. That would be r of t0. That's the point which has to be on that line, plus some parameter times the derivative of r prime at t0. That basically makes sure that from this point you're going to be I can't think of the word that describes that. I mean, it's a tangent line, but some multiple of that first derivative, which is, I think the word I'm trying to think of is slope. Why it would come to mind, I don't know it. The first derivative gives you the slope of the tangent line there. So you're some multiple of that slope. You're at that point at some multiple of the slope there. And that, sure enough, is a tangent line. Okay? Now, this is just sort of my weird way of thinking. Goodness gracious. Okay, I think that's about where I want it. So, what we're talking about, there is the, basically, you think of it as a secant line between those two. And there is the secant line, the change of the secant line over change of time period. Okay? And then if you let the h get closer and closer to 0, you're coming closer and closer to the tangent line. So you see if you let this gets closer and closer here, you see you're approaching the tangent line. But this one gets closer and closer here, then you are indeed approaching the tangent line there. So as the h goes to 0, that blue line approaches closer and closer to the tangent line. And then the equation for the tangent line is this point here, that's your x0, y0, z0, plus some multiple of that tangent line that keeps a tangent to the curve. And can change with different values where you're on the coordinate plane. Okay. Now, I can't get all three of these in one slide, so I'm going to break them up like this. All right. Goodness gracious, my head's going swimming again. And I don't know why. I had lunch, it was fine. Sometimes I think it's low blood sugar. It can't be, I just had lunch. All right, this is showing what I was just trying to do with my fingers. Okay, here's your R of T0, and this is some H time later. You're down to here. This is the difference between these is that divided by a small number is going to make a scalar multiple there. Okay, as your H gets smaller and smaller and smaller, your T plus T0H gets much big, much big. As H gets smaller, 1 over H gets bigger, so your tangent line, and they don't show that it's growing any, but it should be, Okay, as h is getting closer to 0, this tangent line should be getting larger because you're dividing by a much smaller number all the time. Really, it doesn't matter the length of that too much, but ultimately, when you get as far as you can, and this h does tend to 0, then that does give you a tangent line. Now, obviously, it's not an infinite dimension tangent line, so the thing about it growing, don't worry about that. The difference quotient converges to r prime of t, which is tangent to the curve. Okay, that's what we're getting at. That value of it, the length of it, is going to be your magnitude of that velocity vector. Okay. Now, see, all this should have come before the tangent line equation, which we had slides ago. That's that one. Okay. Okay. I hate to do this again, 2 in 1 thing, but maybe I can hang on. What is it, 20 minutes? Yeah, about 20 more minutes. Goodness gracious, my head feels so loopy. But this is example 5, plotting tangent vectors. Okay? Now they say using a computer algebra system. If you have one, use it, but most of the time we don't. And it says plot this vector, r of t. I'm going to zoom in so we can see it better, but I can't write on it when I'm zoomed, so. Why did it do that? I was trying to get it to zoom in, and it just, there we go. Got it. Plot r of t is equal to cosine t sine t 4 cosine squared t. And it says together with its tangent vectors at t equal pi fourths and t is equal to 3/2 pi. Okay. Now, they plotted everything for you. Okay. Let's sort of back up and see if we can make some sense out of it. Couple of things. The x-coordinate can be positive or negative. And you see here, x is positive here. This portion back here can be negative. Okay? Okay. The y-coordinate can be either positive or negative. Okay. Doesn't matter which one you're working toward. If here's your y, and you have some values on the positive side, some on the negative side. Now, of course, there's a limit of how far you go because cosine and sine both only extend as far as 1. And then they go back to negative 1. They periodic like that. So you will have periodic answers here. But the thing to note here, one thing to note, is that your z component is always positive, right? So therefore, you don't have anything where z is negative. Nothing. Nada. None of the values for z can be negative. X's can be positive or negative. Y's can be positive or negative. They are. But z's are only positive because of that component there. Now, I like to start when t is equal to 0. Okay? And I think I'll do a little bit of marking on there. When t is equal to 0, what's cosine 0? 1. So your x component is 1. Okay? So x component is out this axis. Now they show a y component there, but not an x. So let's just say it's out here somewhere, or we'll call it 1. What's your sine of 0? 0. So your y value is 0. So where we must be now, if x is 1 and y is 0, we must be up there. Well, let's see if that fits. 4 times, what's cosine of 0 again? 1 squared is 1, and multiply by 4, you get 4. So sure enough, that's your max, that's your peak there. So there's where we are when t is equal to, oops, gonna have to go back down. Here is about where we are when t is equal to 0. Okay? Weird place to start, but that's where we start. Okay. Let's move on to t is equal to pi halves. Yeah. Yeah, let's just do pi halves. Okay. What is cosine of pi halves? Cosine of pi halves is 0. Cosine starts at 1, and pi halves it goes over to 0. Sine of pi halves is 1. Okay, so your x coordinate is 0, your y coordinate is 1. Okay, there's your positive y. It's a little bit bizarre. X, y, z. If this is positive x, positive y, it has to be back there from 0 to the up. So that's one thing that makes this look a little strange. So, and then cosine of pi halves, of course, is 0, so that 0 squared is 0. 4 times 0 is 0. So there is your z component. So this one over here, down here, will be where t is equal to pi halves. All right. Now, my contention for you here is the function between 0 and pi halves has to be moving down this curve. I can't draw. Okay, let me see if I can get that a little bit better. This ionizing pen is hard to well, okay. Let's just, let me try that one more time. So your, in fact, let me go and erase one more time. All right, let me try it again. As t is increasing from 0 to pi halves, then your function is going down this curve here. I got that a little better that time. My screen still plopped on me. Okay, so it's going in this direction. So it doesn't look at all surprising that pi force would be somewhere in between there. They picked out a point, and that's what they're going to go by. Okay, I'm going to take this off in a minute, but I just wanted to show you where that was. Okay. That is just so messy. Okay, there's t is equal to pi force. Yuck. Okay. Now as we proceed on, let's do t is equal to pi. What's cosine of pi? -1. What's cosine of 0 is 1. Cosine of pi halves is 0. Cosine of -pi is -1. Okay? Now, so the x component is -1. Okay, that's back here somewhere. Positive x this way, negative x that way. Your y component, sine of pi is sine of pi 0. So your y component is 0, so you need either side of that, you're still over the x-axis, and then the z-axis, or z component, is 4 times cosine of 0 is -1. I mean, pi is -1, but when you square it, it becomes +1 multiplied by 4. You're back up here at 4 again. So there's the point when t is equal to, or somewhere approximately, t is equal to pi. Okay? And then down here is 3/2 pi, and then you go back up. So that's the route of your path here. Okay, is around that curve in that direction. Starting up there, going down, up, and back down. Yeah. There's your action there. Now, so I didn't intentionally plot t of pi force. I guess I should have. When t is pi force, what's cosine of t? Cosine of pi force. Square root of 2 over 2. Remember? Okay, that's one of those in between. The only place it could be 1 or 0 is at the coordinate axes. This is in between, so square root of 2 over 2. Sine of pi force is square root of 2 over 2, exactly, same. And cosine then of pi force would be square root of 2 over 2. When you square that, you get square the square root of 2 over 2. Here's what I'm going to do. 1 over root 2. That's the same as square root of 2 over 2, right? And when you square that, you get 1 over 2. Okay, that gives you 1/2, and then 4 times 1/2 is 2. Okay, so that's why this value here, and I'm going to take out this because it's almost a little in the way there. Okay. So this point is root 2 over 2, root 2 over 2, 1/2. No, 2, sorry, 4 times 1/2 is 2. So, it's root 2 over 2 on x, root 2 over 2 on y, so basically you're on the diagonal that goes out here, and then you're up 2. Okay. Now with that being 4, that looks like to me this is too high. Okay? But I can't do much about it. Sort of the way the orientation is. So you won't worry, we'll go from there. Okay. We also wanted to plot, so there's the value at t is equal to pi force. There's the value at t is equal to 3/2 pi. We did this one, we went back and did this one. Again, it looks a little too close up here. It seems like it should be a little further down, but it's okay. Okay, the next thing is a plot. Almost forgetting what the problem was. Goodness gracious. Can't get my eyes to focus on it. Yeah, here it is. Plot R of t is equal cosine t, sine t, cosine squared, force cosine squared t, together with the tangent vectors, okay, at t equal pi fourths and 3/2 pi. Okay, so let's do the tangent vector now. What is r prime of t? Negative sine t cosine t. I can't write. Okay, cosine t. Now the third component's a little more involved. It's not terrible, but it's a little more involved. What would be the derivative of that third component? Okay. Okay. Certainly going to be a 2 times 4, which is 8, cosine t times sine t. Remember, it's 2, yeah. You got to include this one. 2 times 4 is 8 cosine t. Then the derivative of cosine t is minus sine t. So it's a minus 8 sine t cosine t. So the third component is minus 8 sine t cosine t. All right. Whew. Now, let's evaluate that at the pi fourths. So what's this one? Sine of pi fourths? Sine of pi fourths? Square root of 2 over 2, but it's negative, so your tangent vector is going backwards in x, root 2 over 2. That's why I think this dot should be a little further down. Shows a little more negative direction in x. This will be square root of 2 over 2, but that's positive in y, so you're going down, this way in x, but that way in y, which the curve is going that way, so sure, that looks like it's going that way. It's hard to see three-dimensional vector in a two-dimensional plane. It's just hard to see, but it is going. It's going negative in x and slightly positive in y. Neither one of those are very great. But how about this one? When t is equal to pi fourths, what is that value? This is root 2 over 2. That is root 2 over 2. Multiply together, that would be 2 over 4, which is 1/2. So it would be a negative 4. So that's why it's going very sharply negative in the z direction. Okay? A little bit negative in the x, a little positive in the y, but very negative in z. Okay? And sure enough, it's going down here. Okay? Let's move over to 3/2 pi. Okay? What is sine of 3/2 pi? Okay. Sine starts at 0, goes to 1, 0, sine starts at 0, goes up to 1, down to 0. This is at pi halves pi, 3/2 pi, you're at negative 1. Okay? What's your cosine? So sine is, okay, sine of 3/2 pi is negative 1, but it's got a minus in front of it, so it's a positive 1. So it's 1 unit this way. Cosine t, though, at 3/2 pi is, cosine starts at 0, starts at 1, down to 0, down to minus 1, that's a pi, back to 0. So that's a 0. So there is no y component. Okay? And then the z one, this is 1, but that 0, doesn't matter if that's a negative 8, 0 wipes it all out. So there's 0z. So this is just in the x plane, in the x direction, no y deviation, no z deviation. So that is just 1 in the x direction. So there's your tangent vector here. And sure enough, that looks pretty good. If it's coming down up the curve here, down the curve here, then it turns here, and before it goes back up, it's right there at the bottom. It's only going in the positive x direction. It doesn't have a y component, it doesn't have a z component. It's zeroed out here and zeroed out there too, in a sense. Okay. So they did all the work for us, but it's good to go back and see how they got it. Okay. Now, that was sort of arm waving-ish. Don't know if we're going to have time. No, we don't, do we? Yeah. The tangent line itself, from that earlier slide, it was just before it in the book, but it was there here. So what you would do is put your R of T0, and your T0 originally was at pi fourths, and that would be that value, and we did calculate what that was. That was R at pi fourths was root 2 over 2, root 2 over 2, 2. Go back and look at that, and you'll see we said that, plus some t, that's your parameter, times the derivative of it, which was negative root 2 over 2, negative root, or positive root 2 over 2, minus 4. Okay? We did that one. And that's your tangent line. Then you can do the same thing at the other. So next time, sorry we didn't get any further today, we'll do example 6. Okay? And that's at on page 701. And I'm sorry, my eyes were doing such weird things today. Okay. We made some progress in 13.2, though. Homework exercises. How did I get so dirty? I got chalk all over me. Do some of the odd exercises 1 through 5, any of those. Then do any of the odds 7 through 11. Then do 13 or 15 or both. Then 17 or 19 or both. Those are with dot products and cross products, taking derivatives. And then 21. I think you can do that. You should be able to. Yeah. And then 23 or 25 or both. We did that. Do 27. I think that's something we've done. Hold off. No, I think you can do that parameterization of the tangent line. That's what we sort of talked through at the end. Let's actually start there next time. We got all the calculations done, but we didn't actually parameterize the tangent line. So you can hold off on that, and we'll pick up there next time. All right. All right. Just looking ahead a little bit, we've still got 13.3 to do, 13.4 to do. 13.4 is fairly long. Okay. And then 13.5. And I think that finishes 13. No, there is 13.6, but we will talk about it, but we won't do really much on it. Okay? And then I'll have your test ready, which will cover 12.6 and the 5 sections of 13. All right, sorry. I feel like my